Exposed to space, your blood won't boil. You won't freeze instantly. You'll die confused because space doesn't follow the rules. And here is a question. If you could witness any cosmic event in history from a safe distance, what would you choose? Let me know in the comments. I'll pin the most creative answer. Now let's begin. Let's start with something simple. What exactly do we mean when we say space is cold? You've probably heard that space has a temperature of around 2.7 Kelvin. That's about minus 270 degrees Celsius or minus 454 degrees Fahrenheit. To put that in perspective, that's colder than anything we can naturally find on Earth, colder than Antarctica in the dead of winter, colder than liquid nitrogen. It's almost as close to absolute zero as you can get, the point where all atomic motion stops. But here's where things get interesting. That number, 2.7 Kelvin, doesn't come from the emptiness of space itself. It comes from something called the cosmic microwave background radiation, or CMB for short. This is the afterglow of the Big Bang, the faint whisper of energy left over from the moment our universe was born nearly 13.8 billion years ago. Missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Far Infrared Absolute Spectrophotometer, known as FIRAS, have measured this temperature with incredible precision. In fact, recent recalibrations using WMAP data confirmed the CMB temperature to be 2.7260 Kelvin, give or take just 0.0013 degrees. That's astonishingly precise, but let's zoom out for a moment. If you were floating in the middle of interstellar space, far from any star, what would you actually feel? Well, first off, you wouldn't feel anything in the traditional sense because there's almost nothing there to touch you. Space is a vacuum, meaning it's almost completely devoid of matter. There are maybe a few hydrogen atoms scattered across every cubic meter, but that's about it. And here's the kicker. Without matter, there's no way for heat to transfer to you through conduction or convection. Those are the two main ways we experience temperature here on Earth. When you touch a hot stove, that's conduction. When a warm breeze hits your face, that's convection. But in space, neither of those mechanisms work because there's nothing to conduct or convect. So how does heat move in space? The answer is radiation. Everything that has a temperature above absolute zero emits thermal radiation. That includes you, me, stars, planets. Even the cold vacuum of space itself glows faintly with that cosmic microwave background we talked about earlier. Radiation doesn't need a medium to travel through. It's pure energy moving through the void in the form of electromagnetic waves. This is why the sun can warm your face on a summer day, even though there's 150 million kilometers of empty space between you and it. Now here's where the paradox really begins to make sense. Stars like our sun are incredibly hot. The core of the sun reaches about 15 million degrees Celsius. At those temperatures, hydrogen atoms are fusing together to form helium, releasing tremendous amounts of energy in the process. This energy travels outward through the sun's layers, first by radiation in the inner zones, then by convection in the outer zones, and finally it erupts from the surface as light and heat. The surface of the sun, called the photosphere, is still a scorching 5,500 degrees Celsius. But as that energy radiates out into space, something remarkable happens. It spreads out. Imagine turning on a flashlight in a dark room. Right next to the bulb, the light is intense. But as you move farther away, the light becomes dimmer and dimmer. The same principle applies to the sun's heat. By the time you're at Earth's distance, about 150 million kilometers away, the intensity has dropped significantly. Go even farther out past the orbit of Neptune, and the sun looks like just another bright star in the sky, barely providing any warmth at all. Subscribe to this channel and give this video a thumbs up if you're enjoying this cosmic journey so far. Your support helps me bring more amazing content like this to you. So space isn't cold because there's some magical refrigerator out there sucking away all the heat. It's cold because there's nothing there to hold on to the heat. Think of it this way. Temperature is really just a measure of how fast particles are moving. In a hot cup of coffee, the water molecules are jiggling around frantically. In an ice cube, they're moving much more slowly. But in the vacuum of space, there are barely any particles at all. So when we say space has a temperature of 2.7 Kelvin, we're really talking about the temperature of the few particles that do exist there, and the faint radiation field that permeates everything. Now let's talk about what happens when something hot encounters the cold vacuum of space. Take the James Webb Space Telescope, for example. This incredible instrument launched on December 25, 2021, and it's currently orbiting the Sun about 1.5 million kilometers from Earth at a location called the Second Lagrange Point, or L2 for short. Webb's mission is to observe the universe in infrared light, which means it needs to be incredibly cold. Why? Because if the telescope itself were warm, it would emit its own infrared radiation, which would drown out the faint signals it's trying to detect from distant galaxies. But here's the challenge. Even though space is cold, the Sun is still blasting Webb with intense heat. At Webb's distance from the Sun, the solar radiation is incredibly powerful, carrying over 200,000 watts of radiant energy. If Webb were just sitting there naked in space, it would heat up to dangerous levels. So, how do engineers keep it cool? They use a massive sun shield about the size of a tennis court made of 5 ultra-thin layers of a material called Kapton. Each layer is coated with aluminum to reflect heat, and the outermost layers also have a doped silicon coating that gives them a distinctive purple color and extra toughness. These 5 layers work together to create a temperature difference of about 260 degrees Celsius between the hot side facing the Sun and the cold side facing deep space. The hot side sits at around 300 Kelvin, roughly room temperature, while the cold side drops down to about 40 Kelvin, which is minus 233 degrees Celsius. That's cold enough to keep Webb's sensitive instruments operating perfectly. But here's where it gets even more interesting. You might wonder, if space is such a perfect insulator because it's a vacuum, why does Webb need 5 layers? Why not just 1? Great question. While it's true that a vacuum prevents conductive and convective heat transfer, it doesn't stop radiative transfer. Each layer of Webb's sunshield absorbs some of the Sun's radiant energy and re-radiates it, both forward and backward. The next layer down absorbs that re-radiated energy and does the same thing. By the time you get to the 5th layer, the amount of radiant energy reaching the cold side is reduced to just about 1 watt. That's less than a typical nightlight. This principle of radiative cooling is fundamental to understanding why space is cold. Objects in space cool down by radiating away their heat as infrared light. But here's the catch. The rate at which something cools depends on its temperature. When an object is very hot, it radiates energy quickly. But as it cools down, the rate of cooling slows dramatically. In fact, the rate of radiative heat loss scales with the temperature difference to the 4th power. This is why it took Webb several months to cool down to its operating temperature after launch. In the beginning, when it was still relatively warm, it cooled quickly. But as it got closer and closer to 40 Kelvin, each additional degree of cooling took longer and longer. This is completely different from how things cool on Earth. Here, if you leave a hot cup of coffee on the counter, it cools down primarily through convection. The air around the cup absorbs the heat and carries it away. In space, there's no air, so radiative cooling is the only game in town, and it's a slow, patient process. Let me paint you a picture of just how empty space really is. In the best vacuum we can create in a laboratory here on Earth, there might still be millions of particles per cubic centimeter. But in interstellar space, the average density is about 1 atom per cubic centimeter. In intergalactic space, the vast voids between galaxy clusters, it can be as low as 1 atom per 10 cubic meters or even less. That's emptiness on a scale that's almost impossible to wrap your head around. Now, you might think that with so few particles, space would have no temperature at all. But remember that cosmic microwave background radiation we talked about earlier. That faint glow is everywhere, filling all of space uniformly. It's the relic radiation from the Big Bang, stretched out and cooled down over billions of years as the universe expanded. When we measure the temperature of space, we're really measuring the temperature that this radiation field would bring a black body to if it were in equilibrium with it. And here's something truly mind-blowing. That temperature hasn't always been 2.7 Kelvin. In the early universe, just after the Big Bang, the CMB was much, much hotter. As the universe expanded, the radiation cooled. Recent measurements using radio telescopes to observe distant galaxies have actually measured the temperature of the CMB as it was billions of years ago. For example, astronomers observed a quasar called PKS 1830-211, which lies at a redshift of 0.89. That means we're seeing it as it was when the universe was only about half its current age. By analyzing absorption lines from molecules like hydrogen cyanide, or HCN, in the galaxy in front of the quasar, they determined the CMB temperature at that cosmic epoch was about 5.13 Kelvin, give or take 0.06 degrees. This matches perfectly with the predictions from the standard cosmological model, which says the CMB temperature should scale as 1 plus the redshift times the present-day temperature. This is one of the most beautiful confirmations of the Big Bang theory. The universe is expanding, and as it does, the radiation filling it cools down in exactly the way we'd expect. Now let's dive deeper into the heart of the paradox. If stars are so hot, why doesn't their heat just fill up space? Why doesn't the universe feel like a giant oven with all these nuclear furnaces scattered throughout it? The answer lies in understanding how energy spreads out and how incredibly vast the distances in space truly are. Think about our sun for a moment. It's a ball of plasma about 1.4 million kilometers in diameter, and it's producing an absolutely staggering amount of energy. Every single second, the sun converts roughly 600 million tons of hydrogen into helium through nuclear fusion. In this process, about 4 million tons of matter are completely converted into pure energy, following Einstein's famous equation E equals mc squared. That's enough energy to power human civilization for millions of years, and it's happening every second. This energy doesn't just stay in the sun's core, it begins an epic journey outward. In the core, where fusion occurs, temperatures reach 15 million degrees Celsius, and the pressure is 265 billion times Earth's atmospheric pressure at sea level. Photons of gamma radiation are born from these fusion reactions, carrying the energy outward. But the sun is incredibly dense in its core, about 150 grams per cubic centimeter, roughly 150 times denser than water. These photons can't travel far before they collide with another particle, get absorbed, and then re-emitted in a random direction. This creates what scientists call a random walk. A single photon that's born in the sun's core might take anywhere from 10,000 to 1,000,000 years just to reach the surface, even though it's traveling at the speed of light. That's how dense and chaotic the interior of the sun is. The energy moves outward through two main processes, radiation in the inner regions and convection in the outer regions. The radiative zone extends from the core to about 70% of the sun's radius. Here, energy moves through electromagnetic radiation, with photons constantly being absorbed and re-emitted. Beyond that is the convection zone, where hot plasma rises to the surface, cools down, and sinks back down in giant churning cycles, like water boiling in a pot. Finally, the energy reaches the photosphere, the visible surface of the Sun. Here, the temperature has dropped to about 5,500 degrees Celsius, and the photons are finally free to escape into space. They stream outward in all directions at the speed of light, spreading out into the cosmic void. And here's the crucial part: they spread out. Imagine the Sun as a point source of light at the center of an expanding sphere. As you move farther from the Sun, the same amount of energy has to cover a larger and larger surface area. This is called the inverse square law. If you double your distance from the Sun, the intensity of sunlight drops to 1/4 of what it was. If you triple the distance, it drops to 1/9. This is why Mercury, the closest planet to the Sun, receives about 10 times more solar energy per square meter than Earth does, while Neptune, the farthest planet, receives less than 1/900th of what we get. By the time you get out to the edge of the Oort cloud, the distant realm of icy comets that marks the outer boundary of our solar system, about 100,000 times farther from the Sun than Earth is, the Sun's warmth is essentially negligible. Out there, the Sun looks like just another bright star, and the ambient temperature approaches that background value of 2.7 Kelvin. And our Sun is just one star among hundreds of billions in our galaxy alone. The nearest star to us, Proxima Centauri, is about 4.2 light-years away. That's roughly 40 trillion kilometers. Even though Proxima Centauri is also a star, albeit a smaller and cooler one than our Sun, its energy has spread out so much over that vast distance that it contributes virtually nothing to the temperature of the space around our solar system. Speaking of vast distances, if you haven't watched my video on the terrifying distance to Andromeda, I highly recommend checking it out after this one. It really puts into perspective just how mind-bogglingly huge the universe is and how isolated everything truly is out there. The link is in the description and on the card above. This is the reality of the cosmos. Space is unimaginably vast, and the sources of heat, while incredibly powerful, are separated by distances so enormous that their influence diminishes to almost nothing. The energy density of starlight in interstellar space is extraordinarily low. In fact, if you were to capture all the starlight falling on a square meter in the depths of interstellar space for an entire year, you'd collect less energy than a single light bulb produces in a few seconds. But let's get back to the fundamental question. What is temperature, really, in the context of space? On Earth, we experience temperature through the motion of molecules. Air molecules crash into our skin, transferring their kinetic energy to us. The faster they're moving, the hotter it feels. In a solid, atoms vibrate in place, and the faster they vibrate, the higher the temperature. But in the near-perfect vacuum of space, there are so few particles that this concept starts to break down. Let me give you some numbers to illustrate just how empty space is. In the interstellar medium, the gas between stars in our galaxy, the density ranges from about 0.1 to 1 atom per cubic centimeter in the cold, dense molecular clouds, down to about 0.001 atoms per cubic centimeter in the hot, diffuse regions. For comparison, the air you're breathing right now contains about 2.7 times 10 to the 19th molecules per cubic centimeter. That's 27 followed by 18 zeros. Even the best vacuum chambers we can build on Earth still have about 10 to the 6th particles per cubic centimeter. Space is literally billions of times emptier. So when we talk about the temperature of interstellar space, we're often talking about different components. There's the temperature of the sparse gas that does exist, which can actually vary wildly. In cold molecular clouds where new stars are forming, temperatures can be as low as 10 Kelvin. But in the hot plasma surrounding massive stars or in supernova remnants, temperatures can soar to millions of degrees. Yet even at millions of degrees, this gas is so diffuse that if you were immersed in it, you wouldn't feel hot because there are so few particles colliding with you to transfer that energy. Then there's the radiation field, which includes not just the cosmic microwave background, but also starlight, infrared radiation from dust, and other sources. An object sitting in space will eventually reach an equilibrium temperature where the energy it absorbs from all sources equals the energy it radiates away. In interstellar space, far from any star, that equilibrium temperature is determined primarily by the CMB, which is why we say space has a temperature of about 2.7 Kelvin. But near a star, things are different. Consider Earth. Our planet is constantly bathed in sunlight, absorbing energy at a rate of about 1,360 watts per square meter on the side facing the sun. At the same time, Earth radiates energy back into space as infrared radiation. The balance between absorbed sunlight and emitted infrared determines Earth's average temperature, which is around 15 degrees Celsius at the surface. Without our atmosphere, which traps some of that infrared radiation in what we call the greenhouse effect, Earth's average surface temperature would be about -18 degrees Celsius. The Moon provides an even more extreme example. With no atmosphere to moderate temperatures, the lunar surface facing the Sun can reach 127 degrees Celsius during the day, while the night side plunges to -173 degrees Celsius. This dramatic swing illustrates the power of radiative heating and cooling in the vacuum of space. Now let's talk about something absolutely fascinating that's at the cutting edge of physics, the quantum nature of the vacuum itself. For a long time, scientists thought of the vacuum as truly empty, a void containing absolutely nothing. But quantum mechanics tells us something radically different. The vacuum isn't empty at all, it's seething with activity. According to quantum field theory, pairs of particles and antiparticles are constantly popping into existence and annihilating each other in the vacuum. These are called virtual particles, and they exist for such incredibly short periods of time that they don't violate the conservation of energy thanks to Heisenberg's uncertainty principle. This phenomenon is known as quantum vacuum fluctuations, and it's not just a theoretical curiosity. It has real, measurable effects. One of the most famous manifestations of vacuum fluctuations is the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force. Why? Because the vacuum fluctuations between the plates are restricted to certain wavelengths that fit between the plates, while outside the plates, all wavelengths are present. This creates a slight imbalance in radiation pressure, pushing the plates together. This effect has been measured in laboratories and confirmed to high precision. But here's where things get even stranger. There's a theoretical prediction called the Unruh effect, proposed by Canadian physicist William Unruh in 1976. It states that an observer who is accelerating through empty space would perceive it as warm, even though a stationary observer would see it as cold. The temperature you measure depends on how fast you're accelerating. This sounds like science fiction, but it's a direct consequence of combining quantum mechanics with relativity. The Unruh effect has never been directly observed because the accelerations required to produce a measurable temperature are extraordinarily high, far beyond what we can achieve with spacecraft or particles in accelerators. However, recent breakthroughs from researchers at Hiroshima University and Stockholm University have proposed realistic experimental setups using superconducting circuits and atoms in optical cavities that might finally detect this elusive effect. Published in Physical Review Letters in 2025, these studies suggest that we might soon have experimental confirmation of quantum warmth in empty space. Why does this matter? Because it shows us that our everyday concepts of temperature and empty space break down at the intersection of quantum mechanics, relativity, and thermodynamics. The universe is far stranger and more subtle than our intuitions suggest. Another mind-bending aspect of vacuum physics involves something called vacuum energy or zero-point energy. Even at absolute zero temperature, quantum fields still possess a minimum amount of energy due to those vacuum fluctuations we talked about. This energy is thought to fill all of space, and it might be related to dark energy, the mysterious force that's causing the expansion of the universe to accelerate. Astronomers have known since the late 1990s, thanks to observations of distant supernovae, that the universe's expansion is speeding up rather than slowing down. This discovery, which earned the Nobel Prize in Physics in 2011, suggests that space itself is infused with a form of energy that acts like anti-gravity. The leading candidate for this dark energy is the cosmological constant, which could be related to the energy of the quantum vacuum. However, there's a huge problem. When physicists try to calculate the expected value of vacuum energy from quantum field theory, they get a number that's about 10 to the 120th power larger than what we observe. This discrepancy between theory and observation is sometimes called the worst prediction in the history of physics, or the vacuum catastrophe. It's one of the deepest unsolved mysteries in cosmology, and it tells us that despite all our progress, we still don't fully understand the nature of empty space. But let's bring things back to the practical. How do spacecraft and satellites deal with the extreme temperature challenges of space? It's a fascinating engineering problem because, as we've discussed, you can't rely on convection or conduction. Everything has to be managed through radiation. Spacecraft have what are called thermal control systems. These systems are designed to keep the internal temperature stable, usually somewhere between -10 and +30 degrees Celsius, depending on the specific requirements of the instruments and electronics on board. There are two types of thermal control: passive and active. Passive thermal control uses materials and design features that don't require power. This includes things like multi-layer insulation, which is similar to the sun shield on the James Webb Space Telescope. These blankets consist of multiple layers of reflective material separated by insulating spacers. They prevent heat loss through radiation, while also protecting against incoming solar radiation. Another passive technique is surface coatings. Shiny, reflective surfaces emit less thermal radiation than dark, matte surfaces. Engineers carefully select paints and coatings based on their optical properties to control how much heat a spacecraft absorbs and emits. The International Space Station, for example, uses radiators to shed excess heat. These are large panels positioned to face away from the sun. They radiate heat into the cold of space, keeping the station's systems cool. The ISS orbits Earth at an altitude of about 400 kilometers, which means it's still within the fringes of Earth's atmosphere and experiences some atmospheric drag, but more importantly, it's constantly moving in and out of Earth's shadow. When the station is in sunlight, temperatures on the sun-facing side can reach 121 degrees Celsius. When it's in Earth's shadow, temperatures can plummet to -157 degrees Celsius. That's a temperature swing of nearly 280 degrees Celsius every 90 minutes as the station completes each orbit. Active thermal control systems use power to move heat around. Heat pipes are one common technology. These sealed tubes contain a fluid that evaporates at the hot end, carrying heat along the pipe, then condenses at the cold end, releasing the heat. The condensed fluid is then pumped back to the hot end to repeat the cycle. The ISS also uses a more complex system involving ammonia coolant loops that circulate through the station's modules, collecting heat from equipment and transporting it to the radiators. For deep space missions, thermal management becomes even more challenging. Consider the Voyager spacecraft, which launched in 1977 and are now traveling through interstellar space, more than 15 billion kilometers from the Sun. At that distance, solar panels would be useless because sunlight is far too weak. Instead, Voyager uses radioisotope thermoelectric generators, or RTGs, which produce electricity from the heat generated by the radioactive decay of plutonium-238. These RTGs also serve as heaters, keeping the spacecraft's instruments warm enough to function in the frigid environment of deep space. As the plutonium decays, the power output slowly decreases. NASA engineers estimate that Voyager 1 will run out of power to operate any single instrument sometime around 2036, nearly 60 years after launch. The Parker Solar Probe, on the other hand, faces the opposite problem. Launched in 2018, this spacecraft is designed to fly through the Sun's corona, getting as close as 6.1 million kilometers from the solar surface. At that distance, the probe experiences temperatures of about 1,370 degrees Celsius. To survive, it uses a specially designed heat shield made of carbon composite material that's about 11.4 centimeters thick. This shield keeps the instruments behind it at a comfortable room temperature, even while the shield itself glows red-hot. These engineering marvels demonstrate humanity's ingenuity in conquering the temperature extremes of space. But they also illustrate the fundamental principles we've been discussing. Radiation is the only way to transfer heat in a vacuum, and managing that radiation is the key to survival. Now let's explore another fascinating aspect of why space is cold: the role of energy density. When we think about hot things, we usually think about concentrated energy. A flame is hot because it's a region where chemical energy is being released rapidly in a small volume. The core of the Sun is hot because nuclear fusion is concentrating enormous amounts of energy in a relatively confined space. But space is the opposite. It's characterized by incredibly low energy density. Even though the total amount of energy in the universe is staggering beyond comprehension, really, it's spread out over such vast volumes that the energy density in any given region is extremely small. Let me give you some numbers. The energy density of the cosmic microwave background radiation is about 4 times 10 to the negative 14 joules per cubic meter. That's a decimal point followed by 13 zeros and then a 4. To put that in perspective, the energy density of sunlight at Earth's distance from the Sun is about 4 joules per cubic meter, which is already pretty diffuse. The CMB is 10 trillion times less dense than that. The energy density of starlight in the Milky Way galaxy, averaged over all space between stars, is even lower, roughly 10 to the negative 15 joules per cubic meter. And in the vast voids between galaxy clusters, the energy density drops to nearly undetectable levels. These voids, which can be hundreds of millions of light-years across, are the emptiest places in the known universe. They contain a few scattered galaxies, some thin filaments of hot gas, and not much else. The energy density there is dominated almost entirely by the cosmic microwave background and dark energy. This brings us to a profound realization. The universe is mostly empty and cold. The hot, energetic regions like stars, accretion disks around black holes, and the interiors of planets are rare exceptions, tiny islands of warmth in an ocean of cosmic coldness. Even within galaxies, the overwhelming majority of space is cold and dark. If you were to randomly place yourself somewhere in the Milky Way, the chances are overwhelming that you'd find yourself in a region far from any star, floating in darkness at a temperature just barely above absolute zero. But here's something that might surprise you. Even in these cold, empty regions, there's still a story unfolding. Interstellar space isn't completely empty. As we mentioned earlier, there's about 1 atom per cubic centimeter on average, mostly hydrogen with some helium and trace amounts of heavier elements. These atoms aren't uniformly distributed. They clump together in clouds, some cold and dense, others hot and diffuse. Cold molecular clouds are particularly fascinating. These are regions where hydrogen exists not as individual atoms, but as molecular hydrogen, H2, paired with other molecules like carbon monoxide, ammonia, and water. Temperatures in these clouds can be as low as 10 Kelvin, just 7 degrees above absolute zero. They're shielded from starlight by dust grains, making them some of the coldest natural environments in the universe. Yet paradoxically, these clouds are stellar nurseries. Within their frigid depths, gravity slowly pulls matter together. Over millions of years, these clumps grow denser and denser until their cores become hot enough to ignite nuclear fusion, and a new star is born. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such stellar nursery. Located about 1,340 light-years from Earth, it's a vast cloud of gas and dust where thousands of new stars are forming. Observations from telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Array have revealed intricate details of this process, showing protoplanetary disks around young stars where planets are beginning to form. These observations remind us that the cold of space isn't just a static void, it's a dynamic environment where structure and complexity emerge. The coldness allows matter to cool and condense, fighting against the dispersive effects of heat and pressure. Without the cold of space, stars couldn't form, planets couldn't coalesce, and life as we know it couldn't exist. Let's talk about another extreme environment, the space near black holes. You might think that the vicinity of a black hole would be cold given that black holes themselves don't emit light. And you'd be partially right. The black hole itself, the event horizon and everything inside it, is black because not even light can escape its gravitational pull. But just outside the event horizon, things get extraordinarily hot. As matter spirals into a black hole, it forms what's called an accretion disk. Friction within this disk heats the material to temperatures of millions, sometimes even billions of degrees. The accretion disks around supermassive black holes at the centers of galaxies can outshine the combined light of all the stars in those galaxies. These regions, called active galactic nuclei or quasars, are among the brightest objects in the universe. The Event Horizon Telescope collaboration made history in 2019 by capturing the first image of a black hole's shadow, specifically the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. This black hole has a mass equivalent to 6.5 billion suns. The glowing ring visible in the image is the hot accretion disk, with temperatures estimated at billions of degrees. Yet just beyond this inferno, in the regions not actively feeding the black hole, space quickly returns to its typical cold, empty state. Black holes also have a theoretical temperature themselves, though it's extraordinarily low. In 1974, Stephen Hawking predicted that black holes emit thermal radiation due to quantum effects near the event horizon. This is now called Hawking radiation. The temperature of this radiation is inversely proportional to the black hole's mass. For a stellar mass black hole, say 10 times the mass of the Sun, the Hawking temperature would be about 10 to the -8th Kelvin, 100 million times colder than the cosmic microwave background. For a supermassive black hole like the one in M87, the temperature would be even lower, around 10 to the -17th Kelvin. These temperatures are so low that Hawking radiation has never been detected, and it's unlikely we ever will for astrophysical black holes. But it's a beautiful example of how quantum mechanics and general relativity intersect in the most extreme environments. Now let's consider the future. The universe is expanding, and that expansion is accelerating due to dark energy. As galaxies move farther and farther apart, the average temperature of the universe continues to drop. The cosmic microwave background is cooling as the universe expands, following a well-understood relationship. The temperature is inversely proportional to the size of the universe. Right now, the CMB temperature is 2.725 Kelvin. A billion years from now, it will be slightly cooler. 10 billion years from now, cooler still. In the unimaginably distant future, trillions upon trillions of years from now, when the last stars have burned out and black holes have evaporated through Hawking radiation, the universe will approach what's called heat death. In this scenario, the temperature everywhere will be nearly uniform and extraordinarily close to absolute zero. The universe will be a cold, dark, and nearly empty expanse where nothing interesting can happen because there's no temperature gradient to drive processes. But let's not get too depressed about the heat death of the universe just yet. That's so far in the future that the timescales involved make the current age of the universe seem like the blink of an eye. We're living in what cosmologists call the stelliferous era, the age of stars, and we have many billions of years left to enjoy it. Instead, let's talk about something closer to home and more immediate, how the coldness of space actually enables life. This might seem counterintuitive at first. After all, life as we know it requires warmth, liquid water, and energy. But the cold vacuum of space plays an essential role in making Earth habitable. Think about it this way. The Sun is constantly pumping energy toward Earth, about 174 petawatts, that's 174 followed by 15 zeros. If Earth had no way to get rid of this energy, it would just keep heating up until it became uninhabitable. But Earth maintains a relatively stable temperature because it radiates excess energy back into space as infrared radiation. The cold vacuum of space acts as a heat sink, a place where Earth can dump its waste heat. This balance between incoming solar radiation and outgoing infrared radiation determines Earth's temperature. Scientists call this radiative equilibrium. The greenhouse effect caused by gases like carbon dioxide, water vapor, and methane in our atmosphere makes Earth warmer than it would be otherwise by trapping some of that outgoing infrared radiation. Without any greenhouse gases, Earth's average temperature would be well below freezing and liquid water wouldn't exist on the surface. But too much greenhouse effect, like what happened on Venus, can turn a planet into a hellish inferno. Venus is a cautionary tale about runaway greenhouse warming. Despite being farther from the Sun than Mercury, Venus is actually hotter, with surface temperatures around 467 degrees Celsius. That's hot enough to melt lead. The reason is Venus's thick atmosphere, 90 times denser than Earth's, composed almost entirely of carbon dioxide. This creates such a powerful greenhouse effect that Venus can't radiate enough heat into space to cool down. The coldness of space is there, waiting to absorb the heat, but Venus's atmosphere won't let it escape. Mars, on the other hand, demonstrates the opposite problem. With a thin atmosphere only about 1% as dense as Earth's, Mars has very little greenhouse effect. Surface temperatures average around -63 degrees Celsius, and they can swing by as much as 100 degrees between day and night. Mars can radiate heat into space very efficiently, perhaps too efficiently for comfort. Earth sits in what astronomers call the habitable zone, sometimes nicknamed the Goldilocks zone, where conditions are just right for liquid water to exist on the surface. But it's not just about distance from the Sun. It's about the delicate balance between absorbing energy from the star and radiating energy into the cold vacuum of space. This balance extends beyond Earth. Every planet, moon, asteroid, and comet in the solar system is constantly engaged in this dance of absorption and emission. Jupiter, for example, actually emits more energy than it receives from the Sun. How is that possible? The answer lies in gravitational contraction. Jupiter is slowly shrinking under its own gravity, and this releases heat. The planet radiates this internal heat into space along with the reflected sunlight. Saturn's moon Enceladus provides another fascinating example. This small ice world, only about 500 kilometers in diameter, has geysers at its south pole that spray water ice and vapor into space. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through these plumes and analyzed their composition. Scientists discovered that Enceladus has a subsurface ocean of liquid water beneath its icy crust, kept warm by tidal heating from Saturn's gravitational pull. The geysers shoot water hundreds of kilometers into space, where it immediately freezes in the vacuum. Some of the ice particles fall back to Enceladus's surface, but much of it escapes and forms Saturn's E-ring, one of the planet's fainter outer rings. This is a beautiful example of how the cold of space interacts with warm liquid water to create spectacular phenomena. The rapid cooling when the water hits vacuum causes it to crystallize instantly, creating tiny ice particles that reflect sunlight and make the ring visible. Europa, one of Jupiter's moons, is another world with a subsurface ocean. Recent observations from the Hubble Space Telescope and radio observations from ground-based observatories have detected what appear to be water vapor plumes erupting from Europa's surface. NASA's upcoming Europa Clipper mission, scheduled to launch in October 2024 and arrive at Jupiter in April 2030, will study these plumes in detail and assess Europa's potential to harbor life. The fact that these moons can maintain liquid water so far from the Sun, where sunlight is 25 to 50 times weaker than it is at Earth, demonstrates that internal heat sources can be just as important as stellar radiation. But even so, these worlds still radiate their excess heat into the cold vacuum of space. Without that heat sink, the internal heat would build up, and the thermal balance would be completely different. Let's shift our perspective now and think about the larger structure of the universe. We've talked about how individual objects like stars and planets interact with the cold vacuum around them, but what about the universe as a whole? Is there a temperature gradient across cosmic scales? The answer is surprisingly no, at least not at the largest scales. The cosmic microwave background, which we've mentioned several times, is remarkably uniform. When astronomers measure the CMB temperature in different directions across the sky, they find it's the same to within 1 part in 100,000. This uniformity is one of the strongest pieces of evidence for the Big Bang theory and the subsequent period of rapid expansion called cosmic inflation. However, there are tiny temperature fluctuations in the CMB, typically only a few millionths of a degree. These fluctuations are incredibly important because they represent the seeds of all the structure we see in the universe today. Regions that were slightly denser than average in the early universe had slightly higher temperatures. Over billions of years, gravity amplified these tiny differences, pulling matter together to form galaxies, galaxy clusters, and the cosmic web of large-scale structure. The South Pole Telescope in Antarctica and the Atacama Cosmology Telescope in Chile have been mapping these CMB fluctuations with extraordinary precision. Recent data from the South Pole Telescope's third-generation camera, SPT-3G, published in Physical Review D in 2026, analyzed observations from 2019 and 2020. These measurements have refined our understanding of the universe's age, composition, and evolution. The data confirms that the universe is about 13.8 billion years old, consists of about 5% ordinary matter, 27% dark matter, and 68% dark energy, and is geometrically flat on large scales. These observations also provide precise measurements of the CMB temperature and its polarization, helping us understand conditions in the very early universe. Just 380,000 years after the Big Bang, when the universe first became transparent to light. Before that moment, the universe was so hot and dense that photons couldn't travel freely. They were constantly scattering off electrons in what's called a plasma. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms, and suddenly photons could travel unimpeded. Those photons have been traveling through space ever since, cooling as the universe expands, and they're what we detect today as the cosmic microwave background. So in a very real sense, when we measure the temperature of the CMB at 2.725 Kelvin, we're measuring a relic from the beginning of time itself, cooled down over 13.8 billion years of cosmic expansion. The coldness of space today is a direct consequence of the Big Bang and the expansion that followed. Now let's explore what happens at the boundaries between hot and cold in space. These transition zones are where some of the most interesting physics occurs. Consider the heliopause, the boundary where the solar wind from our Sun meets the interstellar medium. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at speeds of about 400 to 800 kilometers per second. As these particles travel outward, they carry the Sun's magnetic field with them, creating a bubble around the solar system called the heliosphere. At a distance of about 120 astronomical units from the Sun, roughly 120 times Earth's distance from the Sun, the solar wind pressure equals the pressure of the interstellar medium, and the heliopause forms. This is where the solar wind abruptly slows down and heats up as it crashes into the sparse gas of interstellar space. Both Voyager 1 and Voyager 2 have crossed this boundary, with Voyager 1 entering interstellar space in August 2012 and Voyager 2 following in November 2018. The temperature structure at the heliopause is complex. The solar wind itself has a temperature of about 100,000 Kelvin, measured by the kinetic energy of its particles. But remember, it's so diffuse that it wouldn't feel hot to the touch. At the heliopause, the collision between the solar wind and the interstellar medium creates a shock wave where temperatures spike to over 1,000,000 Kelvin. Yet just beyond this boundary, in the interstellar medium itself, the temperature drops to a few thousand Kelvin, still much hotter than the 2.7 Kelvin of the radiation field, but cooler than the shock region. This illustrates an important point. In space, you often have to distinguish between the temperature of particles, measured by their kinetic energy, and the effective temperature of the radiation field. A single proton moving at high speed has a lot of kinetic energy and could be said to have a high temperature, but if there's only one proton per cubic meter, the energy density is still incredibly low. Similar transition zones exist around other stars. Massive hot stars produce powerful stellar winds that can be millions of times stronger than the Sun's. These winds plow into the surrounding interstellar medium, creating vast bubbles of hot, ionized gas. When these stars eventually explode as supernovae, they blast material outward at speeds of thousands of kilometers per second, creating expanding shock waves that heat the surrounding gas to tens of millions of degrees. The Crab Nebula is a beautiful example. This is the remnant of a supernova that was observed by Chinese and Arab astronomers in the year 1054. The explosion was so bright that it was visible during the daytime for several weeks. Today, nearly 1,000 years later, the debris from that explosion is still expanding outward at about 1,500 kilometers per second. The nebula glows across the entire electromagnetic spectrum, from radio waves to gamma rays, powered by a rapidly spinning neutron star at its center, called a pulsar. The pulsar at the heart of the Crab Nebula is spinning at about 30 times per second, and as it does, it acts like a cosmic lighthouse, beaming radiation outward along its magnetic poles. This pulsar wind energizes the surrounding nebula, accelerating particles to nearly the speed of light and creating temperatures of millions of degrees. Yet just a few light years away from the Crab Nebula, space returns to its typical, cold, quiet state. The energy dissipates, spreads out, and fades into the cosmic background. These dramatic examples show us that space isn't uniformly cold. It's a patchwork of different temperature regimes, from the frigid molecular clouds where stars are born, to the million-degree coronas of stars, to the billion-degree accretion disks around black holes. but the overwhelming majority of space, the vast volumes between these energetic regions, remains cold and empty, dominated by that ever-present 2.7 Kelvin glow of the cosmic microwave background. Let's talk about something that ties all of this together: entropy and the second law of thermodynamics. This law states that in any closed system, entropy, which is a measure of disorder, always increases over time. Heat naturally flows from hot objects to cold objects, never the reverse, unless work is done to make it happen. This is why your coffee cools down when left on the counter and why ice cubes melt in warm water. The universe as a whole obeys this law. Energy is constantly flowing from concentrated, ordered forms like the nuclear fuel in stars to dispersed, disordered forms like the low-energy photons of the cosmic microwave background. Stars are constantly converting ordered nuclear energy into disordered thermal radiation. Galaxies are gradually using up their gas supplies to form stars. Black holes are accreting matter and, through Hawking radiation, very slowly evaporating into low-energy particles. This one-way flow of energy from order to disorder, from hot to cold, is what gives time its arrow. It's why we remember the past but not the future, why eggs break but don't spontaneously reassemble, why stars shine and eventually burn out. The coldness of space is the ultimate destination for all this energy. Space is the cosmic garbage dump where waste heat goes to die. But here's something profound. This process of entropy increase is also what makes complexity possible. The flow of energy from hot to cold creates opportunities for interesting things to happen along the way. Life on Earth, for instance, is powered by the flow of energy from the hot sun through Earth's biosphere and eventually into the cold of space as infrared radiation. We're temporary eddies in this energy stream, complex structures that exist because of the temperature gradient between our star and the cosmic cold. Without the coldness of space, without that thermal sink to dump waste heat into, none of this would be possible. The universe would reach thermal equilibrium, everything at the same temperature, and nothing interesting could happen anymore. So in a very real sense, we owe our existence to the fact that space is cold. Let's explore another fascinating consequence of space's coldness: the preservation of information across cosmic time. When we look at distant galaxies billions of light years away, we're seeing them as they were billions of years ago because light takes that long to reach us. The coldness and emptiness of space means that light can travel across these vast distances without being significantly absorbed or scattered. The photons that left a galaxy 10 billion years ago arrive at our telescopes today, carrying essentially the same information they started with. This wouldn't be possible if space were filled with hot, dense matter. Those photons would be absorbed and re-emitted countless times, scrambling the information they carried, but the cold vacuum acts as a perfect transmission medium, allowing us to see directly into the past and reconstruct the history of the universe. The Hubble Space Telescope has taken advantage of this property to peer deep into cosmic history. The Hubble Ultra-Deep Field, an image created by pointing the telescope at a tiny patch of seemingly empty sky for over 11 days of exposure time, revealed thousands of galaxies, some of them more than 13 billion light-years away. We're seeing these galaxies as they appeared when the universe was less than 1 billion years old, in the early stages of galaxy formation. The James Webb Space Telescope, with its larger mirror and infrared sensitivity, is pushing even deeper. Webb can detect light that's been stretched to infrared wavelengths by the expansion of the universe, allowing it to see the very first galaxies that formed just a few 100 million years after the Big Bang. Early results from Webb, released throughout 2022 and 2023, have been nothing short of astounding, revealing mature-looking galaxies at much earlier times than theoretical models predicted. This is forcing astronomers to rethink our understanding of how galaxies form and evolve. All of this cosmic archaeology is possible because space is cold, empty, and transparent. The photons from these ancient galaxies have been traveling through the void for billions of years, cooling along with the expansion of the universe until they finally reach our telescopes and tell us their stories. Now let's discuss a question that often comes up. If space is so cold, why don't spacecraft just freeze instantly? The answer lies in understanding the difference between temperature and heat capacity. Temperature measures the average kinetic energy of particles, but heat capacity measures how much energy is required to change an object's temperature. When a warm spacecraft is in the cold vacuum of space, it doesn't have direct contact with the cold environment because there's almost nothing there to conduct heat away from it. The spacecraft can only lose heat through radiation, and as we discussed earlier, radiative cooling is relatively slow, especially for objects that aren't extremely hot. This is actually a problem for spacecraft designers. It's often harder to keep spacecraft cool than to keep them warm because there's no air or water to carry heat away quickly. Astronauts in spacesuits experience the same thing. The vacuum of space isn't conducting heat away from them. In fact, the primary thermal challenge for spacewalking astronauts is overheating, not freezing. The human body generates about 100 watts of heat just from metabolism, and when you're doing physical work, that can double or triple. Spacesuits have complex cooling systems with water-cooled undergarments that circulate chilled water against the astronaut's skin to carry away excess heat. This heat is then radiated away from the suit's outer surface. If an astronaut was somehow exposed to vacuum without a spacesuit, they wouldn't freeze instantly like you see in science fiction movies. The immediate dangers would be lack of oxygen and the expansion of gases in the body due to the pressure difference, not freezing. Freezing would take many minutes or even hours because heat loss through radiation is relatively slow for a human-sized object at body temperature. This principle also explains why insulated containers like thermoses work so well. A thermos has a vacuum layer between its inner and outer walls. Since there's no air in that gap, heat can't transfer by conduction or convection, only by radiation, which is much slower. Your hot coffee stays hot for hours because it's losing heat at the slow rate of radiative cooling. Let's turn our attention now to one of the most exciting frontiers in astronomy, the search for exoplanets and the quest to find life beyond Earth. The coldness of space plays a crucial role in making planets habitable, and understanding thermal physics is essential to assessing whether a planet might support life. Astronomers have discovered over 5,000 confirmed exoplanets as of 2024, with thousands more candidates awaiting confirmation. These planets orbit stars other than our Sun, and they come in an amazing variety of sizes, compositions, and orbital configurations. Some are gas giants larger than Jupiter, orbiting extremely close to their stars, completing an orbit in just a few days. Others are rocky worlds similar to Earth, orbiting in their star's habitable zone. The concept of the habitable zone, which we mentioned earlier, is fundamentally based on temperature. It's the region around a star where a planet with an Earth-like atmosphere could maintain liquid water on its surface. Too close to the star, and water boils away. Too far, and it freezes solid. The boundaries of the habitable zone depend on the star's temperature and brightness. Around a hot, luminous star like Sirius, the habitable zone would be much farther out than around a cool, dim red dwarf star. But it's not just about distance. A planet's atmosphere, rotation rate, axial tilt, and even the presence of a large moon can all affect its surface temperature. Venus is technically within the Sun's habitable zone, but its runaway greenhouse effect makes it completely inhospitable. Mars is near the outer edge of the habitable zone, and it might have had liquid water on its surface billions of years ago when it had a thicker atmosphere. The TRAPPIST-1 system, discovered in 2016 and 2017, provides a fascinating laboratory for studying habitability. This system has 7 Earth-sized planets orbiting an ultra-cool red dwarf star about 40 light-years from Earth. 3 of these planets orbit in the habitable zone. The James Webb Space Telescope has begun characterizing the atmospheres of these planets, searching for signs of water vapor, carbon dioxide, methane, and other gases that might indicate habitability or even life. Detecting life on an exoplanet is an enormous challenge. The most promising approach is to analyze the planet's atmosphere for biosignature gases, chemicals that are produced by life and wouldn't naturally exist in large quantities otherwise. On Earth, oxygen is the most obvious example. Our atmosphere is 21% oxygen, but if life disappeared tomorrow, geological processes would remove that oxygen within a few million years. The presence of large amounts of oxygen, especially combined with methane, which reacts with oxygen, would be a strong indicator of biological activity. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch in May 2027, and ground-based facilities like the extremely large telescope currently under construction in Chile, will dramatically improve our ability to study exoplanet atmospheres. These instruments will be able to detect fainter signals and analyze atmospheric composition in much greater detail than is currently possible. But here's where the coldness of space becomes crucial again. When we observe an exoplanet's atmosphere, we're typically looking at the spectrum of light from the host star that passes through or reflects off the planet's atmosphere. Different molecules absorb and emit light at characteristic wavelengths, creating a spectral fingerprint. To detect these subtle signals, we need the space between us and the exoplanet to be as transparent as possible. Any intervening material would contaminate the signal. Fortunately, interstellar space is remarkably transparent, at least at most wavelengths. The cold, diffuse interstellar medium doesn't significantly absorb or emit light in the visible and near-infrared parts of the spectrum. There is some absorption at specific wavelengths, particularly by neutral hydrogen and certain molecules, but astronomers have mapped these absorption features and can account for them. The transparency of space also enables another powerful technique for studying exoplanets: direct imaging. This involves actually taking a picture of the planet itself, separating its faint light from the overwhelming glare of its host star. This is extraordinarily difficult because a star can be billions of times brighter than the planet orbiting it. It's like trying to see a firefly next to a searchlight from thousands of kilometers away. To achieve this, astronomers use instruments called coronagraphs that block out the star's light, and sophisticated image processing techniques that suppress the star's glare. Several exoplanets have been directly imaged this way, mostly young, large gas giants that are still hot from their formation and emit significant infrared radiation. These planets are easier to detect because their thermal emission makes them relatively bright in infrared wavelengths compared to reflected starlight. As these directly imaged planets cool down over millions of years, radiating their heat into the cold vacuum of space, they become progressively harder to detect. This is why most of the directly imaged exoplanets we've found are young, only a few tens of millions of years old, still warm from their birth. Now let's shift gears and talk about one of the coldest places in the entire universe, not in deep space, but actually here on Earth, or rather in orbit around Earth. Scientists have created temperatures colder than anything naturally occurring in the cosmos using laboratories on the International Space Station. The Cold Atom Laboratory, or CAL, delivered to the ISS in May 2018, creates clouds of atoms cooled to within a fraction of a degree above absolute zero. At these incredibly low temperatures, atoms lose almost all their kinetic energy and begin to behave in bizarre ways governed by quantum mechanics. They form what's called a Bose-Einstein condensate, where thousands or even millions of atoms merge into a single quantum state and act as one superatom. Bose-Einstein condensates were first predicted by physicists Satyendra Nath Bose and Albert Einstein in the 1920s, but they weren't created in a laboratory until 1995, when researchers at the University of Colorado Boulder and MIT independently achieved condensation using rubidium and sodium atoms. This breakthrough earned the Nobel Prize in Physics in 2001. Why do this research in space? Because in the microgravity environment of the ISS, these ultra-cold atoms can be studied for much longer periods without interference from gravity. On Earth, even though the atoms are extraordinarily cold, they still fall under gravity and drift out of the experimental apparatus within a fraction of a second. In space, they can float freely for many seconds, allowing scientists to perform much more detailed experiments. The Cold Atom Laboratory has achieved temperatures as low as 100 picokelvin, that's 100 trillionths of a degree, above absolute zero. This is far colder than the cosmic microwave background, colder than any naturally occurring place in the universe. It's a testament to human ingenuity that we can create conditions more extreme than anything nature produces on its own. These ultra-cold atoms are being used to test fundamental physics, including Einstein's general theory of relativity and quantum mechanics. By precisely measuring how atoms behave at these temperatures, scientists hope to detect subtle effects that might reveal new physics beyond our current theories. For example, ultra-cold atoms can be used as incredibly sensitive sensors to detect gravitational waves, the ripples in space-time predicted by Einstein and first detected by the LIGO Observatory in 2015. Speaking of gravitational waves, let's talk about how the coldness and emptiness of space enables this revolutionary new way of observing the universe. Gravitational waves are produced by accelerating masses, particularly by violent cosmic events like colliding black holes or neutron stars. These waves stretch and compress space-time itself as they pass through, but the effect is incredibly tiny. Even the waves from a collision of two black holes, each dozens of times more massive than the Sun, stretch distances here on Earth by less than 1,000th the width of a proton. Detecting such minuscule distortions requires extraordinarily sensitive instruments and an environment free from vibrations and noise. The LIGO detectors, located in Louisiana and Washington State, use laser beams traveling through 4-kilometer-long vacuum tubes to measure these tiny changes in distance. The detectors must account for countless sources of noise, from seismic vibrations to thermal fluctuations in the mirrors. Future gravitational wave observatories will take advantage of the vacuum of space to achieve even greater sensitivity. The Laser Interferometer, Space Antenna, or LISA, scheduled for launch in the mid-2030s, will consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. Laser beams will travel between the spacecraft, and the system will detect gravitational waves by measuring tiny changes in the distances between them. In space, LISA won't have to contend with seismic noise, atmospheric turbulence, or many of the other disturbances that limit ground-based detectors. The cold vacuum provides an ideal environment for this delicate measurement. LISA will be sensitive to gravitational waves from supermassive black hole mergers, systems that are too massive and slow to be detected by ground-based observatories. It will open a completely new window on the universe, allowing us to observe cosmic events that are invisible in electromagnetic radiation. The coldness of space also plays a role in another cutting-edge area of physics, cosmic ray research. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. They originate from various sources, including supernova remnants, pulsars, active galactic nuclei, and possibly even dark matter annihilation. When these cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that rain down on the surface. Ground-based detectors can measure these particle showers and reconstruct the properties of the original cosmic ray. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah are the world's largest cosmic ray observatories, covering thousands of square kilometers with detector stations. But to study cosmic rays directly, before they interact with the atmosphere, scientists have placed detectors in space. The Alpha Magnetic Spectrometer, or AMS, mounted on the International Space Station since 2011, is a precision particle detector that measures cosmic rays above the atmosphere. In the cold vacuum of space, the AMS can detect particles without the complications of atmospheric interference. The AMS has collected data on billions of cosmic ray events, providing unprecedented detail about their composition, energy spectrum, and arrival directions. Among its findings are hints of possible dark matter signatures in the form of excess positrons, the antimatter counterpart of electrons at certain energies. The interpretation of these results is still debated, with alternative explanations involving pulsars or other astrophysical sources, but it demonstrates how space-based observations can probe fundamental questions about the universe's composition. The vacuum and coldness of space are essential for these measurements. In the upper atmosphere, particles constantly collide and interact, creating background noise that can obscure subtle signals. In the near-perfect vacuum above the atmosphere, particles can travel freely, making their detection and identification much cleaner and more precise. Let's return to stars for a moment and explore something truly remarkable: how the life cycle of stars is intimately connected to the cosmic cold. Stars are born in cold molecular clouds, live out their lives fighting against gravity by burning nuclear fuel, and when they die, they return most of their material to the cold interstellar medium, enriched with heavier elements forged in their cores. This cycle has been repeating for billions of years, gradually enriching the universe with elements beyond hydrogen and helium. The first stars that formed after the Big Bang, called population 3 stars, contained only hydrogen and helium because nothing else existed yet. These massive, short-lived stars quickly burned through their fuel and exploded as supernovae, scattering heavier elements into space. Subsequent generations of stars, called population 2 and population 1, incorporated these heavier elements. Our Sun is a population 1 star, relatively young at only 4.6 billion years old, and it contains about 2% heavy elements by mass. Everything heavier than helium in your body, the carbon in your DNA, the calcium in your bones, the iron in your blood, was created inside stars that lived and died before our Sun was born. This process of stellar nucleosynthesis requires the extreme temperatures and pressures inside stars, but it also depends critically on the coldness of space. When a massive star explodes as a supernova, it blasts material outward at thousands of kilometers per second. This debris crashes into the surrounding interstellar medium, creating a shock wave that sweeps up gas and dust. Over time, this material cools down, radiating its energy into space. As it cools, it can condense into new clouds where the next generation of stars will form. If space weren't cold, if there weren't a thermal sink for this energy to flow into, the ejected material would remain hot and dispersed, unable to collapse under gravity to form new stars. The coldness enables the cooling enables the collapse, and the collapse enables star formation. It's a beautiful cycle powered by the temperature difference between stellar interiors and the cosmic void. The Atacama Large Millimeter Submillimeter Array, or ALMA, located in the Chilean Andes at an altitude of 5,000 meters, is specifically designed to observe these cold molecular clouds. ALMA consists of 66 radio antennas that work together as a single giant telescope, observing millimeter and submillimeter wavelength light emitted by cold dust and molecules. If you made this far, I'm sure you will love this other video on the screen. Why the universe makes it impossible for any two civilizations to ever meet. They're out there, thousands, maybe millions of civilizations, and we'll never meet a single one. See you there.